production. And as you probably know, so this is a compulsory elective course targeted at computer science engineering students. This is the outline. So we'll start with the organization of the lecture. Then I will talk a little bit about motivation. Actually, I think motivation is maybe the most important part of everything, because motivation tells you what this is all about. So why is there interest in the topic? So if you don't have motivation, you don't really know why you should do this and not something else, right? Our time is valuable, so you want to know what the purpose is of what you're doing. So motivation is something which I think cannot be stressed enough. And then we'll talk a little bit about what is cluster computing and big data. What is this field? What is the domain? How has it developed over years and years and decades? And where is it going? And then we will close with a summary and outlook. First let me introduce myself a little. So I'm a professor for software engineering at the Department of Computer Science at the Hochschule Bonn-Rhein-Sieg in University of Applied Sciences in St. Augustine, Germany. Maybe some of you have already visited our university, or have someone of you been at the Hochschule Bonn-Rhein-Sieg already? Not yet. So, but I guess there is the opportunity to do so. So maybe you can apply for a semester at our university. So it's a beautiful place. I can only recommend it. So about the Hochschule Bonn-Rhein-Sieg, it's a public university of applied sciences. Public means it's basically state-financed, so there are also some private universities in Germany, so this is a public university, so it's a state governmental funded. There are about 9,000 students at our university and 150 professors. Of course, there is other academic staff as well. We have 3 campuses. They're all located near Bonn or Cologne. I mean, Bonn maybe most of you have heard of Bonn, which is it was the capital city of Germany until 1990, which also some time ago. But Cologne is the largest city which in the Cologne area. Actually, the northwest of Germany is not so well known to tourists, so but it's actually a very beautiful area to be. So if you happen to come to Germany, don't miss the west. Because most people know about the south very well, like Munich, this area. I've lived some time in Munich as well. And but the west is often a place where most tourists will not happen to come to. So this is Hochschule Bonn-Rhein-Sieg. We have 40 study courses, and if you look at the overall range, I'd say we are a mid-sized university, so not really big, but not really small. So some about this course, so the target group of course are computer science students at ETO, so you, and the location is here. So but it's maybe a bit redundant, because if you wouldn't be here, then you wouldn't be able to read this. The schedule, the course frame is from December 15th to December 31st. Monday, Tuesday, and Wednesday, so this week and the following 2 weeks. Every Monday, Tuesday, and Wednesday. We have 2 time slots on Monday and Wednesday, and 1 time slot on Tuesday. Well, in my schedule it said 8:45, but I learned that actually it starts at 9, so consider this to be 9. So we start at 9 in the morning here to 12 p.m. And I'd suggest to have a 15 minutes break, like from 10:50 to 10:30. So that we have some time to recover. And then we continue from 10:30 to 12. And the second time slot starts at 1 p.m. Also with a 15 minutes break from 2:30 to 2:45 p.m. and then ends at 4:15 p.m. So maybe a little bit earlier if you are fast, so it depends on the contents. Also the same goes for the Tuesday and the Wednesday time slots. Okay. There are some exercises in this course, and actually I reserved like half of the time of every time slot for exercises. Why so much? So you may not need all of this time, but I think it's very important that you are able to reconsider what you've learned, and therefore at the beginning of each exercise you get a time to finish an exercise sheet. I will upload the exercise sheet to the Moodle page, and you should work at this exercise sheet in small groups of up to 3 students. So they're fine together in small groups of up to 3 people, and should aim for 3, but maybe there are smaller groups talking about. The time available differs, but as a rule of thumb, I would suggest that you will take about half an hour to finish this exercise, which will be here in the course. And of course, you can split the tasks between the individuals of the group if this is suitable. And after that, we will discuss the exercise together. And you will also introduce your solutions. So the tasks will be presented by the teams. And so everyone can volunteer to present their solution. And afterwards, I will also show you a sample solution, which I think would be a way to solve the task, but this must not necessarily mean that it's the only way or the best way to solve the problem, right? So there are other ways to solve the problem. It's just a suggestion how to solve the problem. Of course, I will at the end of the day, I will also upload the sample solutions to the website so you can have a look at it later. At some point, the exercise will also include writing code. So we won't start right away with coding, but most computer science students are happy to code, right? So it's basically when they are studying. So during the exercise, I will of course be available to help you if you want, if you need assistance with setting up the environment or if there are any technical problems. You should have an IDE ready, preferably IntelliJ IDEA, and also a notebook, to run the IntelliJ, but not today. Okay? And I will tell you in advance, but so you won't need to do today. But at some point of the course, we will do this, and then you can start coding. And to do that, you first need to set up the environment because you will be running cluster computing frameworks, which will need some kind of setting up efforts. And the assessment. So there were like 47 participants involved in this course. So there will be, so not because I like written exams more than oral ones, the opposite is true, but 47 is too much for oral exams. So there will be a written exam, but later, so the grade will only depend on the result of the exam. This is also important. So no points are assigned to the exercises. There's also no grade for the exercises. So feel free to work on the exercises as you like, and there's no kind of assessment involved with working on the exercises. So no grade for the exercises, no points. Your grade entirely depends on the written exam. The exam date is still to be determined. It will probably be mid of January 2026. And yeah, so the exam will probably be written here at VGU, and I will get your exam sheets then and process them. But I won't be here in person to help you with the exam. So, because I will be in Germany anyway. But the exam will take place here, I guess. Yeah, about literature, this is a basic book I would recommend to this lecture. It's about web-based dynamic MLT services. It's a book about cloud computing. Well, it's not the only source of information, and it's certainly not sufficient for this lecture, but it's something which could help you in understanding this domain. There is a VGU Moodle course site, which you probably have already found. If not, then you can take a note of this link. All documents which are related to this course will be found on the Moodle course site. Also, I guess there is a self-registration on this website, and did have all of you used the self-registration already? You know about it? Okay, so I'm not so familiar with the process here, but I learned that there is a self-registration, so please use the self-registration to document your attendance in this course on the website. As the course progresses, I will upload the lecture PDFs and also the exercise and also the sample solutions to the exercise to this Moodle site. I will start after this lecture. I will start with the first exercise sheet, so you can work on it today. If there should be any announcements, I will also communicate them via the site, so that you will get a notice. Yes. What are the intended learning outcomes? First is I want you to have a thorough understanding of the domain of cluster computing and big data. I'll talk more about what is the domain of cluster computing and big data, of course. Which includes a good understanding of common clustering algorithms. So clustering algorithms are actually very essential part of big data processing, because it usually involves analyzing large amounts of data, so bulk data, and in order to analyze large amounts of data effectively, you need a good understanding of clustering algorithms. That's why we will talk about clustering algorithms also today. Also a knowledge of the technical structure of a cluster and of basic concepts of cluster computing frameworks. So I will of course introduce you further what that means, but basically in order to run a cluster you need to be aware of its technical structure and also about how to set up the components so that they can efficiently work together, which is actually in detail can a very, I won't say troublesome, but it can very challenging task to do to actually make this cluster work efficiently and not only make it work. So make it work can also be troublesome, but in order to really effectively process big data, you need to set up a cluster in a very efficient way. And cluster computing frameworks are some kind of high-level abstraction which enable you to use such a cluster effectively without going too much into technical details, which is the focus of this course. So are there actually some other approaches towards cluster computing which are more like low-level oriented? I will also talk about this a little, but it's not the focus of this course. Okay, so this is something which goes more into the area of scientific computing, and this is something which is not so generic and not so widely used as cluster computing frameworks. And we will also see why cluster computing frameworks are so widespread in this area. I mean, always like the low-level stuff is more, will actually obstruct you from what you want to do often. So high-level abstractions are very, very useful most of the time, unless you exaggerate it too much. There's also like over-abstraction sometimes, but in this case, it's a very, very good thing to have these abstractions. I want you to be able to model problems in such a way that they can be solved efficiently by a clustering system. So why did I write this here? Well, often if you just model a problem in a certain way, it may work on a single machine or a single thread, technically speaking, a single thread, but it doesn't scale. So by which I mean that if you want to solve a problem efficiently on a cluster, the basic idea is that you will multiply the execution by introducing parallelism. And in order to perform parallelism efficiently, you need to model problems in a certain way so that they can actually make use of this parallelism. And that is something which doesn't go for free, and you need to think about a lot to actually model a problem in such a way that it can be solved efficiently in parallel. Because if you don't, then your problem will just not speed up if you use a cluster instead of a single machine. So we need to think about this a lot. A bit more in detail, I want you to be familiar with the programming concepts of Apache Spark-based software solutions. Apache Spark is the most used high-level cluster computing framework today. There are some others, also some more historical ones. Very well-known, let's say, ancestor of Apache Spark is Apache Hadoop. You will also talk about Hadoop. But Spark does some things in a different way, and it's usually the more efficient way. So that's why I focus on Apache Spark. So I just wanted to know there are some other frameworks, of course, but I have a heavy focus on Apache Spark, and there are, of course, reasons why I have a heavy focus on Apache Spark, because I want you to be able to use the most distributed and supported software, which is usually on the market. This also includes the knowledge of the role of Apache Spark and, of course, the related system in cluster environments. So Apache Spark is not only a software, it's like more an ecosystem. So there are lots of surrounding tools and environments which are commonly used along with Apache Spark. And they all have some dedicated purpose. And you should also know how this entire ecosystem works and how the things are put together to form an efficient cluster environment, which is not only involves Spark. And also an overview of the software stacks and tools and the tooling commonly used in cluster. So, of course, if you want to run a cluster, you need like an entire stack. So everything from low-level to high-level abstractions. And I want to give you an overview of what is usually used in a cluster environment and why is this used and how is it put together. Okay, so these are some intended learning outcomes, as I said, among others. So hopefully it's not the only thing you will learn here, but it's my main focus. So that's why I want you to be able to be productive and use clusters efficiently, which I hope will help you a lot if you later work at a company and you have a problem which is related to big data problems, then you will be able to actually implement a solution based on the cluster computing framework, which helps you to solve the problem in a very efficient way. Yeah, what are the prerequisites of this course? I don't have formal prerequisites, so I don't require anything from you formally, but yeah, it's actually helpful to have a good knowledge of Java and object-oriented programming. So this course uses examples which are based on Java. It doesn't mean that it's the only way you can use cluster computing environments. For example, Spark is bindings for several languages, not only Java, but yeah, my examples are in Java. But you can, in theory, also use languages like Python. But you should know basic concepts of object-oriented programming, which includes classes and how they relate to objects or instances of classes, concept of inheritance, polymorphism, methods and variables, all the basic programming stuff. So you should have a basic knowledge on object-oriented programming. You should also have some hands-on experience with IDEs, in particular IntelliJ IDEA. That's actually also, I would say, the most used IDE for Java there is. There are some others though, so like Eclipse. So if you really do like Eclipse, you may also use Eclipse. But well, I haven't worked so much with Eclipse in the more recent times. So if you have technical problems, I would be able to help you with IntelliJ. It is either way, it's very handy if you have some hands-on experience with IDEs. But if not, then well, you can get them here also. So it's not a formal requirement, as I said. But it's always very helpful to be able to use IDEs such as IntelliJ for any programming task. Okay, so far about the organization of this lecture. Now I will proceed with the motivation. Before we start, so what are your thoughts regarding big data? Any suggestions? What does it mean? What's big data? No ideas about big data? Come on. Why did you like this course?
Not about data, I'm talking about terabyte, petabyte scale and very highly relational.
Yeah, so you're the thing that big data is more like in the petabyte scale, and yeah. Other suggestions? So it's about the amounts of data, certainly, yes. Are there some other factors, maybe, than size? I mean, what about high performance computing? So have you heard about high performance computing? Maybe? Yeah, I will talk about high performance computing a little. So what comes to your mind when you hear the term cluster computing? So what is a cluster? How many computers are needed to form a cluster? Two or more, yeah. I would agree, yes. Yeah, I mean, there are some differences between cluster and high performance computing, but I will come to that. First let's look about at high performance computing. So there is, you might say, the classic HPC world. So actually, high performance computing is a very old domain. So there have been high performance computers around for many decades, like basically since the 60s, 1960s, the former century. And I mean, of course, what was considered a high performance computer environment in the 1970s would nowadays be much less than your smartphone power, but at this time it was high performance computing, so of course it has shifted what people can actually expect from computing power, but still up to date there's this domain of high performance computing, and there are it basically means that you have a very, very big machine, something like this here. This JURIS. JURIS stands for Unit Results for European Leading Science. So this is one of these acronyms, where people first think about the term and then they think about how they can make up an abbreviation for it. So it's not really sounds strongly like this. Whatever. This is actually it's a high performance computer in Jülich is a small village near Aachen. Aachen is a town to the very, very west of Germany at the border to the Netherlands and Belgium. There's also a very big technical university in Aachen where I studied computer science, the RWTH Aachen. And where Jülich somewhat belongs to this RWTH research cluster. And so they have this very big machines, and as you can see, they supercomputers can also fill like more than one hall. So very, very big machines for it's proprietary technology. So it's not regular PC technology. It's usually they are proprietary techniques built up for a single purpose, with the goal of having incredibly high performance. And the performance increase of supercomputers over time can be seen here in this diagram as logarithmic appearance. So you can actually see, the blue line is the sum, the overall cumulative performance of all supercomputers, and the red line is the performance of the best supercomputer available in the very year. On the x-axis you have the years, and on the y-axis you have the amount of gigaflops. So 1 gigaflop is, I hope you can read it here, so 1 gigaflop is 1 billion floating point operations per second. So 1 billion is actually already a lot. And as you can see, in 1995, the supercomputer was at about 1. So the yellow line is the number 500 of the years. And so the best one was in 1995. It was about 100 gigaflops, and number 500 on the list was number about 1 gigaflop. And all the world's cumulated supercomputing power was like 1,000 gigaflops, so which is, as you can see here, nowadays it's much, much less than 500 on the list as today. So all the power of supercomputers combined was more than 100 times less only 30 years ago than today. So, you're young, so 30 years might seem a lot to you, but actually, if you look at this scale, you can see, it's always the power of 10, so it's a logarithmic scale. So it's a very impressive performance increase you can see here. What are applications for supercomputers? And they're actually somewhat different from cluster computing. Well, for example, supercomputers are used for simulation purposes. As you can see here, this is an FEM simulation. FEM means finite elements materials. So this is a physics simulation, in this case of the deformation of a car during a quantum crash. So you can basically, this is a model of how the metal of the car, how the materials in the car will deform during a crash. And this kind of simulation is heavily used in the industry, or in this case to give you some idea of what happens in a crash without having to crash a car in real, which is very expensive. So crashing cars, each car will cost you like don't know how much this is in wrong, but in euros like 50,000 or so. So one car will cost 50,000 euros. There's not much in the car to crash it, but all the set up, and the experiment will cost you so much. So it's very, very costly to actually crash real cars. So nowadays, of course, you try to simulate crashes. This is much, much cheaper, even though supercomputers are also expensive, but you can reuse them. So if you crash a car, then you can reuse it. So at least I would recommend it. So finite element simulations. This is also a finite element simulation. In this case, it's a pump housing, and you can see a heat distribution here. So what's the purpose of this? So the idea is that if you know the heat distribution, you know how you could actually design this part with less material, which is more efficient. Like if you achieve the same goal with less material, then you are more efficient because metal costs money. So these kind of simulations are often run first, to make it more cost efficient. So you can find out where you need actually the structure and material and where you don't need it. But also to find out where could this part actually break. So maybe it breaks where the biggest heat is. So I don't know in depth about how this changes on the construction of pump housings. Yeah. But basically there are some you can, from this kind of simulation, you can find out how you could improve the design of the part to make it more reliable, more durable, and also more cost efficient. So that's also simulation. And this is the stream modeling of the airflow around the airplane wing, which is, basically, in this case, it's calculated based on the Euler equations, which is a set of fairly complicated equations you can use to model streams. So it's a streaming simulation. And this is also a classical application domain for supercomputers. If you want to design an airplane today, then usually you will completely design it on a computer, and it will take years before the first prototype actually flies. So you won't build a single prototype without investing years into modeling the thing in the computer, so in the CAD software. Of course, because if you look at how flying has started, then people created something and it either worked or not, and if it didn't work, then it were a crash, and often people were dead after that. So not a very intelligent way to do it. Maybe it was the only way to do it back then, but nowadays it's a better idea, to not risk lives and first find out if this thing will actually fly in a stable way before actually put a pilot into it. And, so also it's usually if you nowadays design an airplane, you have very, very rigid constraints on efficiency, on durability, stability, and so on. So because if you want to have want to create a new model, then it must be better than the ones already on the market, and the ones already on the market are actually fairly effective already. So that's why you have to have this kind of simulation. And it's not only a side aspect, it's actually the key part of the job description of an aircraft engineer to do these simulations. And this is another example. So forgive me for giving you so many examples, but I think it's always important to know what are the domains. This is protein folding of proteins, and this is one possible folding of a certain protein. But don't ask me about that one. I'm not a biochemist, but you can do this protein folding to find out about, for example, how a certain type of medication would behave in the biochemistry of the human body. So there are very, very complicated interactions possible, and you cannot really predict what's happening without simulating it. So this is also a very, very much performance required in this case, because there are so many possible options for a protein can fold, and that's why it's also a very large application domain for supercomputing. And lastly, rendering. This formerly also was a domain of supercomputers. I mean, nowadays, all of you probably know this kind of application from computer games. And there has been a very impressive increase in GPU power. So I guess modern games look much better than this image, which is quite dated, I guess. But like 20 or 30 years ago, this was also, even to create something like this, you would need a supercomputer to do it in a considerable amount of time. So what are the application domains of high performance computing, to sum this up? Often it's research, so it's medicine, genetics, you'll see here. Physical modeling, so cosmology also, you could model like what happens if a star explodes at a supernova or something like that. Weather, climate simulation, also very important area. I mean, whether it's interesting that, I mean, it really depends on the region, because I'm not sure if the weather in this area differs so much so from day to day. There are some regions in the world where you have a very stable climate. But for example, in Germany, you have a very random weather, so it can really change from one day to the other very, very extremely. So that's where weather simulations are important. And lots of Germans always look at the weather forecast before they go out. But of course, it depends on the region. Because if you live in the Sahara, for example, I guess the next day will pretty much be the same weather than the one before. By the way, if you look at weather forecasts, an interesting detail is that if you have some kind of prediction, the prediction must be better than 50%. So 50% accuracy to actually have any value, because if you make the prediction that the weather tomorrow will be like the weather today, this is about 50% of cases, even in Germany, it's correct. So if you just if you look at any prediction, it must be better than this 50% to actually have some meaning. Right? That's because all kind of weather situations tend to be stable for some time before they break up. Then materials engineering, as you have seen with this pump housing, chemistry, if you imagine this protein folding application. So this is all application domains of research where you actually need computing power. And what is also common for this kind of application domain is that we have some very dedicated solutions which are specifically designed to meet the needs of this domain. So you have very custom solutions, and all the software stack, the software tooling, and also the hardware is very well crafted to only fit this kind of purpose. So you cannot really use a supercomputer which has been created to solve a problem for medicine. It's not so easy to make it solve another problem. And also in the industry, I've seen crash tests, microprocessor engineering, medication, statistical calculations, like if you want to build a skyscraper or something. Minimization of material use, which is also a very important part of performance, efficiency considerations. Movie rendering, airplanes, ships, trains, trucks, car, everywhere where you need to simulate something, you need a model, and the more detailed your model is, the better it will usually predict what's actually happening in reality. But it always depends on the model, and the problem with models is that science always works with models, and models are always some kind of approaches to model the reality, but you cannot always catch all aspects of reality. And if your model does not contain something which has been critical to explain the behavior of something, then your model will not predict that behavior. So models are always limited, but actually for many purposes like airplanes, the key factors are very well understood. Like I said with the streaming modeling, I mean, airplanes work actually very, very well nowadays, let's say. So the crash rate of airplanes is actually much lower than the one of cars. So it's a very, very safe means of transportation. And this is basically because it's so well understood how the airflow behaves and how the physics work. if you look at the current top 5 of supercomputers, this is from June 2025, so fairly recent data. And you can see here the current cores here. You can see that so the number 1 on the list has 11 billion cores. So that's quite a lot. So as you can see here, that even number 5 has 2 billion cores, which is like 1/5 of less than 1/5 of 11 billion, but still it's in the scale of billions of cores. So if you compare it to what current PCs have, like maybe 8 cores, or I don't know what's the state of the art, something between 4 and 16, I'd say. Depends on how much money you have, but basically in the PC world, it's usually we have multi-core CPUs, which like not much more than 24 cores, I'd say, so per CPU. And you can see here that computers mainly achieve their performance by upscaling the number of cores to an incredible number. So 11 billion is really a lot. Also, if you look at the power consumption of the number 1 on the list, so this is like 30,000 kilowatts. So that's 30 megawatts of power consumption. That's more than a village has. So it's one of the supercomputers consumes more power than an entire town. So it's also very much it comes at a very high cost to actually make this be more efficient even further or faster. It's maybe not so much more efficient. If you look at the power consumption, it's roughly proportional to the performance. So it's not that you actually gain so much efficiency if you would like double the number of cores again in this case. It's just that if you need power, then the only replacement is be more power. But what you can also learn here is that actually financially it's a very risky decision to build and buy a supercomputer, because if you wait 3 years, you will lose like 30% of the value. Because there will always be better computers sometime later. There was this guy, Gordon Moore. I don't know, someone of you heard about Gordon Moore already? More of you have heard of Gordon Moore. Moore's Law, you know it, definitely. Gordon Moore was the, I will come to Moore's Law right now. Gordon Moore was the founder and the former CEO and the chairman. I don't know why how this I got into this. It means chairman, sorry. Of Intel Corporation. So in the US they have like a CEO and chairman are somewhat different roles, but basically it's both mainly the boss of the company, and the CEO is more on the executive level, and the chairman is more on the overview, the steering board level. So Gordon Moore was both. So he was the boss of Intel until 1997. So then he retired. So you can see he lived until 2023. So he died 2 years ago, so not so long ago. And he was the inventor of Moore's Law. And this law postulates that the number of transistors of an integrated circuit doubles roughly every 2 years. So this is often confused with some other statements like the performance doubles every 2 years, which he never said. So it's not about performance, it's basically about integration density. And because the scaling up of performance recently and also in the case before has been achieved by scaling up by increasing the density of transistors, thereby increasing the number of transistors on the line. So because you have limited space, right? If you want to break a microchip, you cannot scale in area infinitely. So you need to have some fixed fixed size, some fixed area, and therefore if you increase the density and create smaller structures, then you will have more transistors, and of course more transistors lead to more performance. That's of course true, but it's more a derivation. It's not the original statement of what more is. As I said, it was about the number of transistors. If we look at the increase of CPU performance, this is a nice graph. I mean, it ends in 2020, but it still holds until today. So what can you see here? On the y-axis, we have the transistor count. So you can see the most recent systems have like 50 billions of transistors, which is pretty much, but 50 billion is a lot. And if you look at, we go back in time here until 1970, we have been in the regions of like thousands of transistors. So this is an incredible increase in transistor count from the CPU, from the Intel 4004, which was one of the first Intel CPUs, up to what we have today. And what you can see here is that this law actually holds through all this time from the 1970s to today. As you can see, it roughly is it's a straight line. You could draw a straight line through it. And the scale is, of course, logarithmically. Yeah. So it's interesting that this law actually holds for such a long time, because it's not a law of nature, right? It's not like Newton's law of gravity or something that always has to be true for forever, right? It's something really, I mean, in contrast, the physics would say that this cannot hold forever, because at some time, you know, there are physical limits, and for example, if you want to, basically it's created by scaling down the size of elements on a CPU. And if you look at nowadays, for example, you have like about 30,000 electrons, which represent a single bit in a flip-flop. So a flip-flop is the basic structure for storing bits. And so only 30,000 electrons represent one bit. This is, I mean, 30,000 may sound like a lot, but it's actually quite few, because the electron is really very, very small. And if it theoretically you would have like 10 electrons representing a bit, then there would be another law called the Heisenberg uncertainty relation, which tells you that you cannot really be sure if the electrons are there or not, because they're somewhat smeared in time and space. So at some point you will not be able to correctly identify if the electrons are there or not, because there are these quantum physical effects, which means that the electrons just channel back and forth. So there must be a limit, and it's certainly not at one electron per bit, but much larger. I mean, technically this means that your signal will have, at some point you have so much noise that you can really make a stable difference between the 0 and the 1. So it becomes like probabilistic, be 1 or 0, and it's not deterministic. So we can see here that it has been really, you know, driven to much to the extremes. And I'm almost certain that over your lifetime you will experience that this will stop. I mean, it will not stop immediately, but it will, you know, flatten, the curve will flatten. So the performance increases will still be there, but they will not be as fast as it has been essentially before. But to be fair, that I mean, all over this time there always have been people who have said like, you cannot really go like until more than this, because there are some laws of physics that will prevent that. So you have to be careful with the power of engineers. So engineers have often proved that physics is wrong about this. But as I said, there are just some fundamental constraints which you cannot overcome. Yeah. So this is Moore's law. There's another law which is much less well known. It's called Grosch's law. As the name suggests, it was a term coined by Herb Grosch. Who was Herb Grosch? Herb Grosch was an engineer at IBM, was dated in 1953, so quite a long time ago. I believe that there is a fundamental rule which I modestly call Grosch's law, giving added economy only as the square root of the increase in speed. That is, to do a calculation 10 times as cheaply, you must do it 100 times as fast. So to put that in other words, it means the performance of a computer increases quadratically with its price. So this was actually true for the time from 1950 to 1970, and also even some time later than that. But it's not true today, so this is why nowadays not many people know about Grosch's law anymore. What does it describe? So basically he said that to have a efficient machine, you have to have a big, expensive machine. So he said a few big, expensive machines are more efficient than many small, not so efficient machines. And this was the approach which was used actually at the time in supercomputers. So supercomputers did not have like millions of cores, but they had only one core usually. But that core was like more complex and more transistors, so more technology advanced than other cores. So it was a quite different approach from today. Today we actually have reached a stage where increasing the single core performance does not really scale up anymore. So we need to do parallel processing to actually achieve more performance. If you look at the evolution of high-performance computing, until the 1940s there were mechanical calculators. Maybe some of you have heard about the SUSE Z1. So it was a German inventor of the mechanical calculation machine in the 1930s. Then in the 1950s, there were baud rate used. Until fairly recently, they have also been used like for TVs. Very recently, like 20 years ago or something. In the 60s, there were transistors. And in the 70s, we already have integrated circuits. And in the 80s, microprocessors were introduced, and PCs, and in the 2000s until today, we have distributed systems. So cluster systems, cloud systems, grid systems, and multi-core CPUs. So as you can see, here we have actually this parallelism being introduced in the world of supercomputing. So starting roughly from the 2000s, not before. So before they had basically the main advantage was in scaling up the single CPU. At the dawn of computers, there were terminal systems with so-called mainframes as servers. That's something like you can see in this image. And later, the concept of fat clients and thin clients was developed. So the basic idea is that thin client is again some kind of downscale PC, which is certainly more capable than the old terminals for the mainframes, but less capable than a fully featured high-performance PC. Fat clients is the opposite idea, that you will offload some tasks to a client, because centralizing all performance can also be costly, and at some point in time, people found out that PCs are very, very capable already, so it would be a waste of performance to not use the power of the single PCs of the clients. So that was when the concept of fat clients became fashionable. Which possibilities do we have for performance increases? I mean, what would you say? What are the main levers, or what are the main screws we can turn on to increase the performance. So what are the main factors for performance increase? Any ideas? No? Yeah?
I think like we have two ways. The first way is to have a single machine and make it much more powerful.
Mm-hmm.
And the other way is we use many more machines and we make them work together.
Yeah, I mean, basically, of course, you have this, yeah. There's also another option which we didn't mention because it's not about the hardware, but about the software. So, the first option which comes to my mind actually is better algorithms, right? I mean, it was true what you said before, it's just another option. So the better algorithms is I mentioned this because it's actually a solution for the problem. Because what is some kind of Darwinism on the market? So unless someone comes around with a better software, you can sell a very bad software and still make money with it. Right? So actually, a lot of software on the market is not good and technically speaking. So in terms of it's always efficient and it uses the best algorithms available. I mean, there are also not algorithms are important for performance, of course, if you want to design the software. There are some other factors as well, like usability, instability, maintainability, and so on. If you look at the performance, then actually the easiest way to solve the problem more efficiently is to improve the algorithms if you haven't done that so far. Because if you look at, I mean, you probably all know this stuff about the complexity of sorting algorithms. So if you have like a naive approach to sorting data, you will never get the efficiency of advanced sorting algorithms. And actually, you can also prove that there is nothing which can be fundamentally better than Quicksort. So it's fundamentally logically constrained. But Quicksort already is actually it scales non-linearly. That's a really great advantage. If you would scale up the hardware, you could get like maybe a linear increase. So, but if you have actually a better algorithm, you can really change this non-linearly. So you can actually have like a quadratic increase in performance. So always the first thing you should do if you realize, I mean, that's usually the motivation for actually using clusters is that you have a problem and you notice that, well, a single machine just doesn't do it. So it's much too much data, and maybe also some other factors. If you want to do very heavy calculations on some data, then maybe the data isn't so much data, but still too much because you want to do so many calculations on the data. So first thing is what you want to do is really the best way to achieve your goal. So look at the algorithms. Yeah? So is it really, do you need this complexity? Maybe you can reduce the complexity of the problem because there might be some easier way to achieve the goal. For example, maybe you only need to sample 1% of the data and do your calculations on this. And if you have the data base is large enough, then sampling, calculating it on a small sample might be sufficient to gain a certain exactness, right? So, so don't underestimate this point. Better algorithms are really the first thing and not the last thing you should think of. So, first think of better algorithms and think is this really the most efficient way in the theoretical computer science way of thinking solve a certain problem. Okay, then the second option would, as you mentioned, would be faster CPU. So how can we achieve faster CPUs? So one fairly obvious way to achieve faster CPUs is higher clock speeds. And actually this was like throughout the entire 90s until roughly like 2005 or so, I would say. It has been the favorite way to increase performance. So there was, especially during the 1990s, there was some kind of race between companies like Intel and AMD. So they, nearly every year, they doubled the clock speeds of their CPUs. And of course, if you double the clock speed of the CPU, then everything becomes twice as fast. Well, not everything, but because there are some caches and cache misses, and so if your calculations, if your program needs to wait until the data have been transferred to the CPU, of course, it's not always the case that every problem is solved twice as fast, only because the CPU is has a higher clock speed, but still, of course, if I run a CPU at a higher clock speed, and also the bus clock speeds have been increased as well. So this is a fairly simple way to increase the performance. I mean, in theory is fairly simple. And the problem is, of course, if the higher you are, the harder this becomes, right? Because there are some physical limits which will actually ultimately limit what you can achieve in total for a clock speed. Then the third option would be, of course, as you mentioned, the parallel processing on multiple CPUs and systems. So, well, we can, if we are able to solve the problem in parallel efficiently, then ideally it would scale with the number of parallel CPUs. And if you want to scale it any further, as I said, there are limits for the number of cores on the CPU. So if you want to increase the parallelism over the number of cores, then we need to scale on the cluster level, which actually means we have several CPUs, but still, in most clusters, every single CPU has also a lot of cores. So because clusters are also more efficient if you have fewer CPUs with many cores than if you have like a lot of systems with few cores. Okay, so we have these three options. There was a guy called Gene Amdahl who made up another law called Amdahl's law. So lots of laws here. So Amdahl's law describes the boundaries of accelerating a program by parallel executions on multiple CPUs. And what we can see here in this diagram is the share of program execution time, which is parallelizable, depending on the number of processors. So we have on the x-axis, we have the number of processors. You can see here is scale to the power of 2. And here we have a linear scale on the y-axis for the speed up. And as you can see here is these four lines are the share of program execution time, which is parallelizable. Because the problem you have is that in reality, not the entire execution time of your program is parallelizable. It's always just a portion of it. It's a part of it. And of course, the theoretical boundary of how much you can scale up in performance depends on the share of program execution time, which is actually parallelizable. And Amdahl states that there is an association between the speed up and the number of processors depending on the parallel portion. You can see here if only 50% of the execution time is parallelizable, then of course you can see our speed up will maybe asymptotically will approach the 2, but will never get higher than 2. I mean, of course, because everything else is consumed by something which cannot be scaled up. If you look at the 90% line, then it's more, but still we have here you can see there is a speed up of factor 10 and not more, because at factor 10 we are at the situation that we cannot accelerate this 10% of execution time which are fixed. So this can be actually brought into a format of a term as seen here. So for example, if a program takes 20 hours of execution time on a single thread, so single execution of so 1 hour execution time cannot be parallelized, and then 95% of execution time can be parallelized. Thus, the minimum execution time is 1 hour, and the highest theoretical acceleration is then 20 times the single thread performance. So in general, it follows this graph here. So the S latency, the theoretical acceleration of execution time, is 1 divided by 1 minus p plus p divided by s, where P is the fraction of execution time of the task that will benefit from the improvement of the resources. In this case here, 0.95. And S is the acceleration factor of the fraction of execution time which profits from the organization. Okay, so this is the theoretical boundary which Amdahl described. And to make this maybe a little more illustrate this problem, imagine we have a painter scenario where one painter needs 1 hour to paint a room. So I guess we agree that 2 painters will only need 30 minutes to paint the very same room, roughly 30 minutes. How long will it take for 20 painters to paint this room? What do you think? Any idea? Sorry? 3 minutes? Yeah, I mean, if you would like, if you have to be able to scale it up, yeah, it could be 3 minutes. But I mean, if you consider this problem in reality, you imagine there are like 20 painters imagine this room, like we have 20 people running around and painting. So I mean, I guess they would like probably obstruct themselves because there are too many people for a small area. So I guess the problem here is that you cannot scale this up infinitely because you have some time of your execution time is actually consumed by the interactions between the painters, and this is somewhat limited. Imagine there are 100 painters, so I'm not sure if they would actually fit in this room, but they'll certainly not be able to paint anything, right? Because they were just standing in the way. So actually, it would even decrease the number of painters at some point. And there is, I don't know what would be the optimum number you could actually achieve here, but I'm not sure it would be way much more than 4 or 5. So maybe 4 or 5 people would be the most efficient way to paint this room. Maybe, I don't know. But I doubt you would be able to increase it any further by using like 50 painters, except 5. Yeah. So you see that this is actually something which also happens with software, because if you want to have parallelism, then it comes at a cost, because you need some processing power, some time of the CPU to actually arrange this, because you need to synchronize the processes. You have some work going on which is only there to actually enable parallelism, but not to solve the actual problem. And this is some kind of overhead which is always there. So that's why you cannot really achieve a scaling factor of 1. So if you, in theory, you would say you have 2 CPUs, except that's 2 times faster than 1, but you will never reach this factor of 2. And that's actually, the reason is actually basically the same as with the painter scenario. So there's something you need to actually synchronize the work. And what are the conclusions for parallelization? I mean, if you look at the painter scenario, what would be the best option you could do if you have like 2 painters or 50 painters would be you have also 50 loops. Because if you would have 50 loops, except 50 loops, not 1, then you would be able to scale up, right? So it would perfectly scale. So if you had 50 painters and also 50 loops, then at 1 painter per loop, then you would be 50 times as fast. But of course, you would need to have the requirement that you want to have painted 50 loops, right? So the idea is that if the problem size increases with the amount of CPUs, then we are in this efficient range, right? Because the more CPUs you have, the larger the amount of data to be processed should be. So this is an interesting insight where we come to another law. So as I said, lots of laws today. It's called Gustafson's law. Yeah, what is Gustafson's law? Yeah, Gustafson, John Gustafson, actually I guess it's a Swedish name, but I'm not sure if he was Swedish or American or Swedish descent, but anyway. Gustafson's law states that every sufficiently large problem can efficiently be parallelized. So that's an interesting insight. It means that if you cannot scale efficiently, basically your problem is not large enough. So that's why that's very nice, because usually big problems are large problems. So it means that if you have a sufficient amount of data, you can efficiently parallelize it. And if you compare it to Amdahl's law, the difference, of course, is that the parallelized portion of the problem increases with the number of CPUs. While in Amdahl's law, it's static, so you have a fixed number, the problem size is fixed. And Gustafson says that the problem size is able to grow. So for Gustafson's law, we have this formula. So the speed up of n, where n is the number of CPUs, is 1 minus p plus n times p, where p is the fraction of execution time of the parallel portion of the program, and the speed up is the acceleration factor. So yeah, of course this is somewhat limited. If you have a problem which cannot be increased indefinitely, then this law is not applicable. So you cannot really apply to the problem. And there are problems which have this structure. Yeah? So it's not applicable to any problem. And yeah, of course, there may be other problems which must be solved in as short time as possible. In this case, you are also limited in how you could scale up the amount of data we process. So there are some problems where Gustafson's law cannot be applied, but of course lots of data in the these are actually the problems of the cluster computing area where this law is applicable, because if it isn't, then you will have a problem in actually scaling up using a cluster. Yeah, so this is basically what I said before with the painter example. So if one painter needs 1 hour to paint a single group, but you cannot solve this problem 20 times faster by employing 20 times more painters, well, you could argue, wouldn't it be better to have a single very performant painter which only needs 10 minutes for it? So, I mean, well, in reality, it's hard to think of a very efficient painter which is like 10 times as fast as a regular painter. I don't know. Maybe there is, but maybe there are competitions for painters. I don't know. But basically, this is something which has been thought of over the development of supercomputers. Today I will I guess we will shift the back a little, but I guess it's a problem. So so there's this famous quote from this guy, Seymour Cray. Seymour Cray was the founder of Cray Computers, which was for I guess like 2 or 3 decades. It was the leading company for building supercomputers, starting from the 1970s. And so Seymour Cray was the founder, the CEO, the overall boss of everything of Cray Computers, Cray Computer Corporation. And there's a famous quote by Seymour Cray who said, "If you were blowing a field, which would you rather use, 2 strong oxen or 2024 chickens?" So, I mean, the analogy is clear, I guess. So, well, if you could argue, okay, I have so many chickens, so they must be very strong because I have so many chickens, but in reality it probably wouldn't work at all, because, well, I don't know if it could make the chickens run in the same direction, but even if so, I'm not sure you would be able to kill the field, right? So, I mean, in this case, probably you would go for the oxen. I mean, what did he mean by this? Of course, he was implying that it's a better idea to have very few very powerful CPUs than very many which are not so powerful. And for a long time, he actually also relied on systems which had only very few but very powerful processors. So, but actually, he changed his mind shortly before his death in 1996, so he died in a car accident. So before that, he actually started the development of a massive parallel system. So it wasn't that he was like, ideologically fixed to this idea or something. It was more that he thought that it was the technically most feasible solution to that. But at some point in time, he actually realized, well, okay, this maybe the chickens are actually better, so this approach doesn't work anymore. So why did the upscaling of this concept come to an end? So what do you think? What was the reason for that? So why didn't it work anymore to increase the power of this very few CPUs? Or not so well anymore? It did still work, but not so well.
Basically, we go back to the painter problem. Like we will only consider that we have one room to paint, so we can replace a 1 hour painter with a simple, very performant 10-minute painter. But if we have 100 rooms to paint, then maybe having a lot of 1 hour painter painting all the rooms at the same time would be much better than trying to employ, 5 people who can paint each room by 10 minutes.
Exactly, and also if you like in this example, you just can't find a painter which is like 10 times as fast as a regular painter. So, and this was the same as CPUs. It became harder and harder to actually scale up the power of the single power performance. So it actually was limited in this regard. And what I find interesting is that Zero Gray actually also realized this, well, very late, but you have to understand that at the time he said this with the Oxen, it was true. So from nowadays we have a different perspective. Right? Okay, so and there are also technical reasons for this. And like in this example, if we have a CPU with a 5 gigahertz clock frequency, it has a cycle of 200 picoseconds. So a picosecond is a very, very small fraction of a second. And this means that, 5 gigahertz is quite a common clock for today's CPUs. I'm not sure if mobile phones already reach this, but they're between 2 and 4 gigahertz range. But you can certainly buy PCs with 5 gigahertz. And this means that within one cycle, a distance of less than 2 centimeters is traveled. So one clock cycle, your signal can only travel this far. And that's not very much, right? If you look at how big the chip is, that's actually a very significant portion of the entire chip distance, right? So this is a problem that actually, if you would scale this up even more, at some point your signal would just not reach the entire chip anymore, just because of the speed of light, which is limited. And also the power dissipation increases quadratically with the clock frequency. So it's not linear, it's actually a quadratic increase, which means that, so if you would like have 10 gigahertz instead of 5, so it would like 4 times more power dissipation. And this, of course, it became a limit, because if you're already if you look at today's most powerful desktop PC CPUs, they are like, they have a power consumption which is in the 100, 120, 200 watt range maybe. So if you would estimate that you would not consume 200 watts but 1,000 watts, then it's impossible to cool down this. Right? So 1,000, maybe it's possible, but it's very, very hard. So we actually, at some point, this power dissipation will be too much to actually cool down in an efficient way. Also, at least in countries like Germany, electricity is very expensive. So maybe you wouldn't want to run a system with so much power consumption, because, as I said, it would be twice as fast but consume 4 times as much electricity. So it's not efficient, right? So, however, modern CPUs do more calculations per cycle than older ones. But of course, even if you could like increase the number of transistors without increasing the clock, but still, if you increase the number of transistors, or if you increase the power per cycle, it also means that you will increase the power consumption. But linearly, not perfectly, but still if you increase power consumption, of course. Because I mean the current needs to flow through more gates. Right? So basically you're gonna making electrons flow around the chip, and it always needs power. So recently scaling efforts in GPUs and graphical processors have dwarfed all other processor designs. So that's why modern supercomputers nowadays rely on a very, very large number of GPUs, as we have seen, like billions of GPUs. And GPUs were originally designed for computer games or graphic processing, but actually they can be used for many other purposes as well. So you can see this upscaling of the clock frequency is not feasible anymore at some point. This is roughly at the 5 gigahertz, so more than 6 or 7 is not really technically feasible. So, I mean, there are of course some experiments you can achieve frequency as high as 20 gigahertz, but not something you would be able to sell as a product. So what is cluster computing and big data? Big data is it's about the amounts of data which are too large or too complex for classic data processing approaches. I mean, of course, it's somewhat related, right? So, either you have very, very large amount of data, then even very simple calculations can be a high effort, right? If you have really like terabytes of data, petabytes of data, then even you would want one very simple transformation on all data, it would become a very expensive operation. But also you could have not so much data, but maybe you want to do something which is computationally very expensive on the data. So with regarding big data, there are also often cited the so-called 3 V's. So what are the V's? The first V is volume. So what does volume mean? Very large amounts of data. Of course, volume is mostly, the term big says it, right? So of course it's about volume. But also variety. What does variety mean? And that's also very important differentiation if you compare to the high performance computing application, because you have a high diversity of data types and data sources. This is not the case if you look at like scientific computing and high performance computing area. You have in the high performance computing area, for scientific purposes, you often have very uniform data. Like, for example, if you have the big accelerators, so they produce really a lot of data, but it's all the same kind of data. It's all the same type of data. And in the classical big data application domains, you have a high variety of data. So you have collected lots of data from different data types, different data sources. Which also means that you have different schemas you would have to apply to the data to store it in the database, for example. And you have velocity, which means that you want to have a high-speed data generation and transfer. So it's also about velocity because often in a big data application, you have also stream processing in such a way that lots of data are flowing in, coming in, and you need to process them in a pipeline, and of course the pipeline needs to be fast enough to deal with this inflow, because otherwise you would not catch up with the inflow. So velocity is also key. So we have volume, variety, and velocity. And also sometimes there's a fourth V, and the fourth V stands for veracity. What is veracity? It means that there are high quality requirements. What could be a high quality requirement? For example, you actually want to inspect and analyze every data point. As I said, actually quite often you could just draw a sample and do some analysis with it, and then assume that this will somewhat model the real distribution accurately enough. So this is actually something which works quite well in a lot of cases, due to the power of statistics, but not always. So there are some situations where you really do need to inspect every data point. And this is, of course, something which is where big data processing comes very handy. Because it's a really big difference if I inspect 1% of the data set or 100% if it's a big data set. So this is curiosity, so you have some kind of high quality requirements to fulfill. So we have challenges on many fields because of this. This is acquisition, data acquisition. For example, if you collect data manually, it doesn't really scale, right? So people would need to enter it manually. It really depends on the application, of course, but data acquisition can be a pretty big challenge. Storage as well, because just the approaches to store data will easily come to limits if you apply them to big data processing. Analysis, of course. If you want to analyze lots of data, then you have to have a very efficient way of analyzing them. Data transfer is also a big challenge because, especially in a cluster, you know that you have some effort to send data from one node in the cluster to the other node. So they are not always everywhere. So the data are somewhat partitioned. So they are somewhat distributed. And so data needs to be transferred. And this transfer is also an additional effort, which wouldn't be there, or at least not at this cost, if you had a single PC, for example. Then you have visualization. I will explain why data visualization is also very important. Then you have data protection, which can also be challenging, especially in areas like the European Union. You have very, very strong data protection laws. So if you want to sell a product worldwide, then you would also need to be aware that there may be different data protection laws, which means that, for example, if you're doing statistics on personal data, then there should not be able to identify individual persons by analyzing this data and so on. So data protection is also a challenge.
Looking at the time, was something.
Okay, so I'll just take 5 minutes and then we'll do a break, okay? What is cluster computing? So in general, it stands for the parallel processing of systems with distributed memory storage. And a cluster consists of nodes, and the nodes represent independent systems. So each node in a cluster is, for example, an individual PC. It can be a PC, it can also be some other kind of hardware. We'll talk about it later. So all the nodes together make up the cluster. And the nodes are connected via a network. There's always some kind of preferably high-speed network between the nodes. If the network is not efficient, then the cluster is not efficient. So you need to have a very efficient connection. I will also explain this in detail why the connection needs to be very, very fast. Often there is a cluster structure. So you have a dedicated master node. And this master node controls the other nodes. So the master node is the control node which you connect to actually offload your cluster program, and then the master node will command the other nodes and distribute the tasks and collect the results. And commonly you also have a shared storage, so all nodes access a shared storage. In addition to individual storage which the nodes usually also have. And the nodes can be all kinds of systems, for example, PCs, or they can also be computers. There are 3 application domains of clusters. high availability clusters, high performance clusters, and high throughput clusters. So what is the difference between them? The high availability, I guess the name basically says it already. So high availability means that you have, you want to maximize availability, so you have redundancy in all components in order to avoid a single point of failure. For example, you may have uninterruptible power supplies. For high performance clusters, you want to upscale the number of nodes and maybe also have more powerful CPUs in the nodes. And high throughput is something which is important for I/O, so input-output related components, especially network and memory. For example, if you have web servers, this is something for high throughput more than high performance, because what limits you is not the performance of the systems, but it's the throughput, because you have many requests, but every request is easy to serve. But the problem is the number of requests. So many requests means you're I/O bound, so you have lots of I/O requests, and in general you can say that this is used for the simultaneous handling of a large number of clients. Okay, so to summarize this chapter, so we learned about the following: the organization of this lecture, the application domains of high-performance computing, the history of supercomputing, some laws, as I said, there's laws, it's not that there's laws of physics or something, describing and modeling the limitations of the parallelization of problems, and the terms big data and cluster computing. Okay, and after the break, well, not after this break, but this afternoon, we will dive down deeper into the world of big data science. So after the break, we will look at the exercise, and then in the afternoon, we will dive down into the world of big data science. Okay, so thanks so far. And then I'd say we have a 15-minute break, let's say like 10:50 or something, and then go on.